Most people think, what is electricity, is a fluid that flows inside wires. But in engineering, this is not correct. In this video, we will understand what is electricity, clearly from the fundamental level. Electricity is not a physical substance stored inside wires, and it is not a fluid that moves through a conductor. In engineering, electricity is a phenomenon that describes the behavior of electric charges when they move under the influence of an electric field. Inside conductive materials such as copper, atoms are arranged in a fixed crystal lattice. Some electrons in the outer shells of these atoms are loosely bound and can move freely through the material. These are called free electrons. When no external force is applied, these electrons move randomly due to thermal energy. There is no preferred direction, so no net flow of charge exists. However, when a voltage is applied across the conductor, it creates an electric field inside the material. This field exerts a force on the free electrons, causing them to move in a slightly biased direction. This directional movement of electrons is what we define as electric current, and the overall phenomenon is what we call electricity. Electricity is therefore not something contained inside wires, but the result of charge motion under the influence of a field. First, consider a conductor without any external source. Inside the material, free electrons already exist and are constantly moving in random directions due to thermal energy. This motion is completely disordered, so there is no net flow of charge. Next, when a voltage source such as a battery is connected, it creates a potential difference between two ends of the conductor. This potential difference generates an electric field throughout the material. This electric field applies a force on all free electrons at the same time. Although each electron still moves randomly, there is now a small bias in their motion toward one direction. As a result, electrons begin to drift slowly through the conductor. This drift velocity is small, but because there are so many electrons, the combined effect produces a measurable electric current. Thus, electricity emerges from the interaction between the electric field and the collective motion of electrons inside a material. A simple way to understand electricity is to imagine a large crowd of people inside a hall. Everyone is moving randomly in different directions. Although there is a lot of movement, there is no overall flow in any specific direction. Now imagine that an exit door becomes more attractive than the rest of the room. People still move randomly, but gradually more people start moving toward that exit. Even though each individual movement is still random, a net flow of people begins to appear in one direction. Electricity behaves in the same way. Electrons inside a conductor are already moving randomly due to energy at the atomic level. When an electric field is applied, it does not create electrons or force them in a rigid path. Instead, it slightly biases their motion. This small bias is enough to create a large-scale directional flow when billions of electrons move together. So, electricity is not a substance flow, but a statistical result of many random motions becoming slightly aligned under an external influence. In electrical engineering, electricity is used as a controlled mechanism to transfer and process energy. A power source, such as a battery or power supply, creates a potential difference that drives current through a circuit. Different components in a circuit interact with this current in different ways. Resistors convert electrical energy into heat, capacitors store energy in electric fields, and inductors store energy in magnetic fields. Semiconductors add control, allowing engineers to manipulate current flow for amplification, switching, and signal processing. From an engineering perspective, electricity is not treated as a physical substance, but as a controlled flow of charge that can be shaped and directed. This controlled charge flow is the foundation of all modern electronics. Without it, there would be no computation, no sensing, and no communication systems. Every electronic device, from simple sensors to complex processors, relies on the predictable behavior of electric current in designed circuits. In RF engineering, electricity behaves differently compared to DC circuits. Instead of flowing steadily in one direction, the electric charge oscillates back and forth at very high frequencies. These rapid oscillations create time-varying electric and magnetic fields. According to electromagnetic theory, changing electric fields generate magnetic fields, and changing magnetic fields generate electric fields. This interaction allows energy to propagate through space in the form of electromagnetic waves. These waves carry information without physical wires, enabling technologies such as radio broadcasting, Wi-Fi, and mobile communication systems. At RF frequencies, electricity is no longer just a current in a wire. It becomes part of a dynamic electromagnetic system that extends into space. Understanding this transition from simple charge motion to wave propagation is essential for all RF engineers because it forms the bridge between circuit theory and wireless communication. So today, we learned that electricity is fundamentally the motion of electric charges driven by an electric field, not a physical substance inside wires. We went from definition, mechanism, intuition, engineering, view, RF application to build a complete understanding of the concept. This foundation becomes even more important when we study voltage, which is the driving force behind this motion. Thanks for watching. See you in the next video.